Hello guys. So in our previous video we talked about understanding the difference between generalized linear model and generalized linear mixed model. So in that video we talked intensively about the differences between these two models and when to make use of either of them. So if you have not watched those videos, before you watch this, go back and watch that video so that you can have a better understanding of what we're doing here. So today I have this data set of different school. We have student ID, that's the first one we're having here. Then we're having school ID, study R, and study test. So we're trying to see if study R has an effect on test scores, to see whether an increase in study R will also bring about an increase in test score, or a reduction in this would also bring about a reduction in this, or whether their relationship is inverse. Okay, so we also have school ID here. So for this our school ID, we're going to use this as a hierarchical data or grouped data to check for random effects for using our GLMM. So like I said, we have explained all this in our previous video. So please, if you have not watched that video, kindly go back and do so. And kindly you can as well drop your comment in the comment section. And if you have not subscribed to the channel, please do so and hit the notification bell to get instant notification once new video is uploaded. So let's go to R and see how we can do this. We can do for the GLM and the GLMM as well. Alright, so here in R we have these codes we are going to be using for this analysis. So first we would have to download and install these packages, the LME4 that is for the GLMM model, as well as the GLM model. Then we also use we have to also install the ggplot, install and load for visualization, and also the deployer for data manipulation, and car. Okay, so the car is useful for model diagnostics and checking collinearity. So now, having done that, we are going to load our data. So my data name is GLMM dataset. Okay, so this is just the description of the pathway my data is saved on my PC. So you can have a different directory for your own data in your own PC. So I will just control enter this. So the read.csv here is reading my data here into R. So when this happens, you would see this loaded in your environment. So from my environment here, you could see that this has successfully loaded, and we're having 500 observation and 4 variable. Okay, so now we proceed to convert the school ID to factors. All right, so here we're going to be considering the school factors, the school ID here, as factor for the random effect modeling. Okay, so and here we have it. This is the code for that, so I'll just control enter this. Now we go to the next line of code, which is to check for linearity. And to check for linearity, we are going to be using a scattered plot to do this. Okay, so I will just control enter this. All right, so this is the result for the scattered plot. So from this scattered plot here, the scattered plot shows the relationship between study hours and test score. So the study hour here, the study hours are here on the x-axis, while the test scores and the y-axis. So each black dot here represents the individual data point, and the blue line, these blue lines here you're seeing is the regression lines, and it captures the overall trend. So the key observations we are having, we can see from this diagram, is that there is a positive relationship, which implies that as study hours increases, test scores also tend to increase, suggesting a positive correlation. Also, we can see that there is some variability. While the trend is upward, there is some scattered around the line. So there is some scattered around the line, indicating that other factors might also influence test scores. All right, so the final observation we can see here is that we have no major non-linearity. So the blue lines follows, as you can see, follows a fairly straight trajectory, which suggests that a linear model might be appropriate for this data set, and that therefore we can also check other statistical checks to ensure that this our data is appropriate and our models are appropriate for this data set. Sorry. All right, so now let's go further to check the correlation. All right, from the R console here, you can see that the correlation is 0.8896027, which is a positively strong correlation. So, you know, of course, our correlation, if we have a correlation close to 1, we have a strong correlation. So from here, you can see that we have a positively strong correlation between study hours versus test score. So this is just reinforcing our scattered plot, the information obtained from our scattered plot. So now let's go to the next one, which is to check for normality of test scores, which is our dependent variable. So we're going to use a histogram to check this. So this is the code we're going to be using for this, and I will just click Ctrl Enter to display the result. All right, so this is the result for the histogram, and here now from the diagram here, we could see that this histogram represents the distribution of test scores among students, and the key observations from this diagram here is the general shape here. So we can see the distribution appears approximately normal, but slightly skewed at the right. Okay, so from this diagram you can see that it's slightly skewed at the right. Secondly, we can see that the majority of the test scores falls between 60 and 100. So majority of the scores falls between 60 and 100, which with the highest frequency around 70 and 80. Okay, the highest around 70 and 80. So also we can observe from here that a few students score below 50 and above, so below 50 and above 110, indicating small variation in performance. So you see fewer students scores in this region as well as this other region here. So now what are the possible implications? So if the goal is to fit a model normality test, so we have to consider doing further tests to ensure that our data is normally distributed. Okay, so for this data we are going to go further to look at Shapiro-Wilkes test for normality. Okay, and also know that this works when we have the observations less than 5,000. All right, so let's do the Shapiro test using this the code here, Shapiro.test open parentheses df, which is what we saved our data as $sign test scores, test underscores. All right, so we just Ctrl Enter this to see the result. So from our Shapiro-Wilkes normality test, we see that the p-value here is less than 0.05. So since it's less than 0.05, the assumptions for Shapiro-Wilkes normality test is that the null hypothesis says that our data is normally distributed. So since we have a small p-value here, we are going to reject the null hypothesis and say that our our data does not follow a normal distribution. So since we have ascertained that our data does not follow a normal distribution, we can now go further to fit a general linear model. And for the general linear model, we are going to be using the gamma, because our dependent variable is continuous, but not normally distributed. So this is the code to fit the generalized linear model. We have the GLM obtained from this package here, the LME4. So the test underscore is our dependent variable, and we have study hours as the factor that determines or influences text score. So we're going to be using the distribution, gamma distribution here. So mind you, gamma distribution is handy when we are having non-negative continuous variables. Okay, so and the data, we are obtaining this information from df, which is what we have saved our data as. All right, so now let's run this and look at the summary. So here is the results for the GLM. So let's do a quick interpretation of this result. All right, so from this result, we can see that the intercept here is 3.985008. So this implies that when study hour is equal to 0, the expected test score is this 3.985008. All right, so and for the study hours, we are having 0.064792. So this implies that for 1 unit increase in study hours, we are having a 6.48% increase in the expected test score. So this is what the coefficients here are telling us. And remember, we are using a log link, and to interpret the coefficient, we would have this interpreted as exponential raised to the power of 0.06472 minus 1, and that will give us approximately 6.48 increase. Okay, all right, so that is that for the GLM model. So now let's go to the generalized linear mixed model. Please kindly note that the essence of this tutorial is to compare between the generalized linear model against the generalized linear mixed model. All right, so now for the generalized linear model, first of all, to fit a generalized linear mixed model, we standardize study hours to improve numerical stability. This helps with model convergence. So this is the code to do that, and we can enter this. Now we can now fit the generalized linear mixed model using the GLMM, and we're having our test scores tilde study underscore hours under scale because we've standardized it, and we are having plus school ID. So this is the random effect per school. All right, and we are also having the family as gamma. Now we run this. All right, so after running this, we now look at the summary of what we have to see our results. All right, so this is our result for the generalized linear mixed model. All right, so let us do a quick comparison between this and the generalized linear model. Let's look at the ICAM result. For the generalized linear model, we're having 3,381.8. Now let's look at the generalized linear model. For the generalized linear model, we're having the generalized linear mixed model, rather, we're having 3,120.3. So we're having a lesser ICAM value, and this suggests a better fit. So the generalized linear mixed model is a better fit, all right, for our data. So let's see. Okay, now let's look at the fixed the fixed model here. Okay, so let's look at the, first of all, let's look at the random effects here. So for the random effects, we're having for school ID, we're having the variance of 0.001741 and standard deviation of 0.04172. So here you can see that the variation between schools here are very small. Now let's look at the residual. The variance is 0.005052 and the standard deviation is 0.07108. So this shows the variability between schools. All right, so now let's go to the fixed effect. For the fixed effect, we are having the intercept as 4.338498 and a study R of 0.174405, and this shows a higher estimate compared to the GLM. Okay, so now in comparing this with the GLM, we can see from the IC value that the GLMM outperforms the GLM, and the GLMM was able to handle our hierarchical data, and also the effect of study hours for the GLM, we had a 6.48% increase per hour, but for the GLMM we're having about 17.4 increase per standard deviation per hour in this case. So also for the GLMM model, it takes into account inter-school variation, but the GLM model does not. So now what we're having here from our script here, you can see the IC value for the GLM and the IC value for the GLMM model. So we can actually have a visualization of the GLM versus the GLM predictions. All right, so let's do that using the code here and then plot it on a graph. All right, so this scattered plot compares the predictions from the GLM and GLMM models for the relationship between study hours and predicted test scores. So the key observations here is 1, trend and fit. So we can observe the red dashed line here. So this red dashed line here represents the GLM predictions, which follows a relatively smooth trend. On the other hand, the blue solid line represents the GLMM predictions, showing more variation around the trend. So now let's look at the GLM versus the GLMM. So the GLM assumes a fixed relationship between study hours and test scores. It provides a more rigid and smoother fit, as we can see here. But then, on the other hand, the GLM allows for random effects, capturing individual level variations and accounting for dependencies in the data. This explains the more flexible and fluctuating blue lines. So this is explained by these blue lines, right? Now, for better model choice, the GLMM here, which is the generalized linear mixed model, the blue lines here, appears to better capture variability in test scores, especially at higher study hours, suggesting it may be a more realistic fit for the data. On the other hand, the GLM, which is represented by this red dash line here, underestimates variations and might account for random effects like student-specific differences. So in conclusion, the GLMM provides a more flexible prediction model by incorporating random effects, which makes it a better choice when data contains nested structures or individual variation. So with that, we have come to the end of this tutorial, and if you have any question, feel free to drop your question in the comment section and I'll do well to respond in time.